Welcome to another session of microengineering. In today's lecture, we are going to discuss the working of TWTA, that is traveling wave tube amplifier. Last lecture, we have seen that TWTA has got a lot of advantages as compared to Klystron. It is a wideband amplifier. It's a broadband amplifier. Gives you 60 dB of gain. If you want to increase the gain, what do? You just increase the length of the tube. Now to understand the working of TWTA, I hope you remember we had a helical structure. We are going to understand about the axial electric field, meaning what does that helical structure do? When we are looking at the helical structure, the equivalent circuit of the helical structure looks like a transmission line. That is the most surprising thing. It looks like a transmission line, which is nothing but a combination of inductor in series and capacitance in parallel. You have seen this. So this increase new type of current is induced. So that induced current, we are taking it as I. Can you see over here? This is I, and infinitesimally small current. That amount of current has to be taken. So this convection current which is newly introduced has to be shown in detail. That derivation I'll show to you now. Fine. How do we establish the derivation is, we have already known that it looks like a transmission line circuit. So we have the transmission line equation to start with. How do you have dabba by dabba z of I, capital I? That will be, if you can say voltage, the voltage across the capacitor minus the newly introduced current. This is that infinitesimally small current which is introduced. Dabba by dabba z can be written as minus gamma. I hope all you know, because whenever wave propagates in z direction, dabba by dabba z is always taken minus gamma. This was explained in rectangular waveguide derivation. You remember this? Dabba by dabba t, we have written j omega, right? This is again gamma. So this is one part. If current you can write, can you write voltage? Yes, you can write the voltage also. So voltage equation came in the same way. Only thing is voltage we normally write in terms of inductor equation and the current in terms of capacitor. So I have just written that. Again, replacing dabba by dabba z by minus gamma and this dabba by dabba t as j omega. What did we do? We are replacing this equation. You got I, no? You have already found out I from where? From here. You got the value of the I. Substitute this equation in this and get me the equation in terms of V. On solving this equation, they found out gamma not to be j omega root LC. Now don't get surprised. This is a transmission line equation, so you will get the equations also in terms of that. For example, ideal transmission line equation gamma naught is equal to j omega root LC. How do you get this? Because gamma is alpha plus j beta. Alpha has to be 0 because attenuation has to be 0. So gamma becomes equal to j omega root LC. That part they have written. So you don't get some price. And of course you have the characteristic impedance that has to be equal to square root of L by C. That is what they derived at the end. That means the total voltage that will be introduced in your transmission line circuit, not the transmission, sorry, your helical structure should be, it's coming as V is equal to gamma naught Z naught upon gamma square minus gamma naught square I. So this is in total, this is the type of voltage we are going to get. This is called a circuit equation because it gives you an idea about the axial electric field of the slow wave helix structure, which is affected by the spatial AC electron. So don't get confused because this is because of your helical structure, the electron movement behaves in a different manner. It induces its own current, and because of that, you have an extra component of gamma also coming into picture. If you have extra component of gamma also coming into picture, can I say gamma alpha is already not there because we say attenuation is very minimum and all. But this gamma will definitely give rise to more beta values now. So this more beta values will try to find out. Alright, so we were discussing about the more number of beta values. You can see over the more number of beta values which you have got, as I predicted, that beta values will be somewhat in this manner. That is 4 propagation constants we are going to get. Those 4 propagation constants are something like this. Can you see over here? 4 propagation constants. Because of that axial convection current, we have got 4 types of propagation constants. Now, let us understand this propagation constants in detail. Very, very important topic. Can you observe this alpha value? Here alpha plus j beta is there. So here alpha some amount of attenuation is there and this is negative value. Now when you're getting a negative value, how you're taking is alpha. See students, alpha is already a negative, alpha is already an attenuation and you're taking it in negative value. What we say is that your wave is propagating in forward direction. How do I know it is propagating forward direction? Because you have got plus j. So wave is propagating in the forward direction. Secondly, you are saying minus alpha. Minus alpha means negative of alpha. Well, attenuation is not there. Attenuation is not there, signal is growing. So when signal is growing in the positive direction, what do you call this? Amplification. So whenever your gamma is working in gamma 1 mode, it is amplification mode. Means TWTA, traveling wave tube amplifier, works in gamma 1 mode. Now let us understand gamma 2. Gamma 2 mode, can you see over here? I'll use a blue color. What is gamma 2 mode doing? It is again same thing written. Again positive direction, but this time it is not minus here. It is positive. And it is positive means your wave is actually getting attenuated. I am putting 10 volts in the input. I am expecting 50 volt because it's an amplifier. I will get 5 volt. Will I be happy? No. So this does not work in an amplification. This does not work in an amplification. What is this thing? Neither attenuation, neither increasing, decreasing. Whatever I have put 10 volt, I am getting 10 volt. Not happy. This mode doesn't work. What is interesting is this mode. In this mode, can you check that it is minus j beta e. So minus j beta e means wave is propagating in backward direction. Please note, backward direction. Wave is propagating in backward direction. What do you call that? Suppose from the source to destination, something is coming back from destination to source. We call it as feedback. And feedback always results in oscillations. Hence, this gamma 4 mode, please note students, very important, this gamma 4 mode always works as BWO. What is BWO? What is BWO? BWO. BWO means backward wave oscillator. Whenever gamma 4 works as gamma 4 mode, it works as a backward wave oscillator. In backward wave oscillator, if your TWTA has to behave as backward wave oscillator, the attenuators which was shown has to be removed. Because if attenuators are there, it will not allow the reflected wave from the load side to come to the source side. So the attenuators will have to be removed. So your diagram of BWO will be exactly same at TWTA. Only difference is that there will be no attenuators. It will be continuously helical structures. Am I clear? Yes. So all the four propagation constants have been explained in detail in this slide. You can go through these things. All these things have been given in microengineering by Samuel Liu. Same thing I have explained in these slides. We can solve one problem. Before solving a problem, there is one formula for power gain. You can just by heart this formula is minus 9.54 plus 47.3 NC, where N over here is circuit length. It is not number of something. It is circuit length, and capital C is called as gain parameter of TWTA. Both formulas are given. So in this question they have asked you gain parameter C, which I told you. This gain parameter normally we get it from your propagation constants only. This formula has to be by hearted by you all. You just have to substitute and get the value. And then you have the output power formula has been given to you right now. You can just substitute and directly you get the answers in terms of dB. They have also asked about the four propagation constants. I hope you remember those four propagation constants. Very important. You just have to substitute in the formulas like this. In this you need to know the value C, you know, it is not small c, it is not velocity of light, it is gain parameter. Please make a note of that. It's gain parameter, please be careful. Beta E is nothing but electronic phase shift constant, which is omega upon V naught. V naught value you know from Klystron we are seeing it is always has to be 0.593 into 10 to power 6 square root of V naught. Omega you know 2 pi f, substitute, get the value of beta E, substitute and get all the four propagation constants. Very important. Normally in questions sometimes we do ask about it. Thank you.